Talking about today then is, kind of clean this up a little bit. We're talking about today then is the common ion effect and buffers. But we've really kind of had this before with that Le Chatelier's principle. And for example, we have some of the best tap water in the country. It comes from an aquifer, right, underground. And the problem is that it's pretty much saturated with this calcium. And it's a problem because they call it really hard water. Now, you would care because it's hard to get soap with hard water. There's a lot of metals and ions in it. So you want to get the soap, you want to get the metals out of there. So some people have a water softener in their house. But the city of San Antonio, they really don't care whether you can wash your clothes or not. What the city of San Antonio is worried about is getting the water from the aquifer to your house without all the underground pipes getting clogged up, right? Getting precipitated out. This stuff, calcium carbonate, it's saturated. Because this is what the aquifer is, right? Water ran through all the calcium carbonate, has all these little channels and big caves underground. So how do you get rid of this? How do you prevent this stuff from precipitating out? Well, just try to get rid of those carbonates. So that's what they add. So they're trying to get rid of the calcium. So they add at the water treatment facility where all this water is pumped into from the aquifer, they're going to add a bunch of sodium carbonate. So if you add a bunch of sodium carbonate, sodium's not going to precipitate out, right? But you can get the calcium carbonate to precipitate out too because you're adding more carbonate. It's that common ion effect problem, right? It's in the equilibrium. So you have too much carbonate, too much product, shift it back to reactants, so you precipitate out the calcium carbonate. And so that's, I mean, with mining, soil science, aquifers, water treatment, common ion effect is a big deal. Buffers, it's just Le Chatelier's principle again, but it's so applicable to talk about controlling pH. Like in your blood is buffered. If you get outside of this narrow pH region, you're in a world of hurt. So your blood itself is buffered. And how does it do it? We'll kind of talk about it, right? Well, we'll talk about the mechanism anyway. And the idea here as well with buffers, they cause problems with acidity in Coca-Cola, but it's probably better off for you to drink that than beer because you don't get addicted to Coca-Cola. But okay, the common ion effect. So let's just jump into this. The below reaction may be used to describe the common ion effect. So if we're going to write HCN, HCN is an acid. So we need to write a Ka reaction for it. So Cameron, how would we write the Ka reaction for HCN? What goes on the reactant side over here? A Ka reaction, the acid has to be on the reactant side. Then everybody on the product is going to be H plus and Cn minus. Right? So the Ka reaction, the conjugate acid gets H plus the conjugate base. It's supposed to be an N. Okay. And we write that because, well, we have HCN. Hey, where does the equilibrium lie here? In other words, Mia, do I have a whole lot of, because I've got a double arrow going on here. Do I have a whole lot of product or do I have a whole lot of reactant? They're assuming you know this. Because HCN is a what type of acid?
I mean, not
It's one of the, is it strong? It's a weak acid. So it's a weak acid. So that means there's hardly any reactant or product. Hardly any product. So they're assuming that you realize this. Before you even start talking about all this stuff, this buffers and common ion effect, that, heck, you have almost all HCN. Maybe a billionth, 1/1000th of these molecules, or 1/40000th of them, actually breaks up into H plus Cn minus, which makes it a little bit acidic. Because, right, it breaks up a little bit, but hardly. It's almost all HCN. It's almost like a precipitate. It's all HCN, except it's dissolved, so it doesn't. You can't see it. Okay, so if the reaction's at equilibrium and each of the following occurs with the total moles of H plus increase, decrease, remain the same. So you hardly have anything in the first place, but you add 25 mils, 0.2 molar HCN. I don't know if you remember this kind of thing in Andromeda, but this is the Le Chatelier's principles. We kind of just rehashed it again. But would you end up with more or less H plus if you add HCN? Remember the game? Everything's hunky-dory. It's at equilibrium. We mess it up by adding too much product or reactant. We add too much reactant. So now it's got to shift towards product. Oh, so then that's the game I play. You got to shift towards products. And you look and see what's a product. Oh, H plus is a product. So H plus has to, what, Jose? Increase, decrease, or remain the same? You added some HCN. You have too much reactant. It's got to shift this way, big time. So it has to decrease. It's going to form it, right? You have too much HCN. It's got to shift over there. So you're going to make more H plus. You're going to make more CN minus because you got too much HCN right now. Just increase it. Just increase it. What if I add some sodium cyanide solid? Jose, see if you can redeem yourself. Sodium cyanide solid. Okay. Kind of a trick question because you're supposed to look and see sodium cyanide and you're not supposed to see it up there because the sodium is supposed to be confusing you. But hopefully it doesn't. Why? The one solubility rule that I said you guys should know. What is it? Do you remember? That's the technical reason. Whenever you see group what, you just ignore it. Group 1. Because its sole purpose there, group 1 is sodium, alkaline, right? Its sole purpose is to make solids that will dissolve 100% in water. That's their sole purpose. So you're not even supposed to look at them, honestly. You're supposed to see, oh, I just added some cyanide. Well, now I've got too much, everybody, product, so it's got to shift towards reactant. So the H plus will decrease. That's the game we're playing. We're going to add 10 mils. Now, I changed this morning, so your notes are all fine. They're all perfect. They're all right. It's just I added a few things to hopefully not muddy the water anymore. But I added 10 mils of 0.085 molar Bowdy HNO3 is added to the solution. What is so special about HNO3? So the world's divvied up into, you recognize the H. So this has to be a what type of compound? An acid. Okay. The world's divvied up into strong acids and weak acids. But there's only how many strongs? 6. So you know those 6 backwards and forwards. And then anything else pops up, and hey, that has to be weak. That's why like HCN, it's not one of the 6. So it's really useful to know those strong acids. Otherwise, it's really hard to do a lot of this stuff. So you see HNO3, and you're supposed to recognize it as a strong acid. It's one of the 6. So it's a strong acid. So that means you really don't care about the NO3 minus. You're adding H plus, right? So if you're adding H plus, right, that equilibrium is going to shift back that way. It's kind of a bad question because we're adding H plus. So that means all H plus has to really net increase. But I should have changed the question to what's the effect on the HCN. But the point is the equilibrium is going to shift that way, right? 5 mils of 1.05 molar calcium hydroxide. So I think that the answer to C is just that the equilibrium will shift this way. Right? So, kind of a bad question. But How about if we had calcium hydroxide? That's not even up there. Calcium's not up there. Hydroxide's not up there. What's so special about this? It will interact. Because you see the hydroxides. Hydroxide is our base. It reacts with H+. So if it reacts with H+, H+ is going to go away, go down, right? Decrease. Okay, so that's kind of the game you're playing with this common ion effect. But the homework really isn't there. The homework is really all with this stuff, these buffer problems, okay? And what we're going to do, our big goal is they're going to give us a buffer, like a can of Coca-Cola. They're going to say, you're going to add a little bit of HCl to it. You're going to add a little bit of sodium hydroxide to it. What's the new pH? Okay. Or you drink, better yet, you drink a can of Coca-Cola, right? And what's the new pH in your blood? Okay, it better not change much, otherwise you're in a world of hurt, like we said. So your system's buffered. A buffer is a solution that has the ability to resist slight changes in, what would you say, Megan? Slight changes in pH when small amounts of acid or base is added. All blanks, Kenneth, how would you guess this one? All blank are mixtures of a conjugate acid and its corresponding conjugate base. Buffers, exactly. A buffer has to have a conjugate acid in it and a conjugate base. Otherwise, it won't be able to resist changes in pH. Any solution of a blank acid may be used as a buffer. Steph. Strong or weak? Now, if you say strong, you're set so that the pH won't change if you add a base. But if you add, because then there's acid to react with it. But if you add more acid, it just gets more acidic. There's nothing to react with it because that conjugate base is too weak. And that's kind of the technical answer. But the answer is weak. The answer is weak because you need appreciable amounts. You need a lot of conjugate acid and you need a lot of conjugate base so that you can go either way. You can have something there that'll react with acids if it's added, react with bases if it's added. So let's see how it does it. Buffer solutions keep their acidity constant, so keep the pH constant, right? You can even change that word to pH if you want. It's going to pretty much stay there. It won't be perfectly constant, but it'll be pretty darn close by reacting with acids and bases that are added to them. So is HF, Cameron, a weak acid or a strong acid? HF is a weak acid. Perfect. So that means this is a buffer. Okay, so this is a buffer. In this system, the conjugate acid is, Mia? HF. And everybody, the conjugate base is F minus. Okay. If a strong acid, Andromeda, we're going to add a strong acid to the buffer, then what would react with that acid, HF or F minus? If we add a strong acid, what reacts with acids? Not another acid. Anybody help her? A base, right? If you add an acid, acids react with bases, bases react with acids. So we're going to add a strong acid, so that means a base has to react. What would that be, HF or F minus? That'd be F minus. So you add a strong acid, F minus reacts. Well, if F minus reacts, Jose, it's going to produce what? HF. See what's going on? F minus reacts with this H plus, and that H plus is from the strong acid, and it forms a lot of HF. Now HF is a much weaker or stronger acid than what was added. Bowdy, what would you say? HF, this is what I kind of changed on your notes. HF is a much, we added a strong acid. We're actually just exchanging a strong acid for a weak acid. So all the strong acid gets converted to a weak acid. Well, a weak acid is much weaker, right? It's much weaker. So since it's a lot weaker, the pH whoa, I missed it here. So only, okay. Now we did it in an acid though. So is that pH going to go down a little bit? I mean, we're talking a really small amount, 0.001 pH units or something. It will increase or decrease if you add an acid. It'll decrease, right? Because really low pH is really acidic. So it'll decrease a really small amount. Not as much as it should have. It should have dropped like a rock. You just added a strong acid. It should go way, way low and get really, really acidic, but it doesn't. You drink that, an acid or a base, your blood pH stays relatively the same. But it will get a little bit more acidic if you do consume acids. Okay. A strong base is added to the buffer. Now what's going to react? Everybody. HF will react. Now HF will react with the base and will produce F minus, exactly. And this is F minus is a much weaker base. So we're exchanging a strong base for a weak base. So now the pH is going to only a really small amount. It's going to increase or decrease. It's going to increase, right? Because really basic is, okay. So let's see if we can follow this. This is where I think it really, this is the part you really want to understand. 250 mils of 0.1 molar HCl is added to this buffer. Okay. So we've got this solution of HF in it. Whoop. All right. Now we don't even know what the concentration is of the HF, but it doesn't really matter. We know that we have some in there. We had 250 mils of 0.1 molar HCl added to the buffer. The number of moles of F minus will what? Because the HCl, you got to get rid of it. It's going to react immediately. It's going to react with what? The HF or the F minus? It's going to react with the F minus. So that means the number of moles of F minus have to decrease, right? Because the F minus has to react. You follow that? HCl is a acid. So it has to react with the base in the buffer. Otherwise, that's the whole purpose of the buffer. So if it reacts with the base, F minus, the moles of F minus has to decrease then. By how many moles, though? The exact same number of moles that you added of the acid. Because everything's 1 to 1. So that kind of makes it easy, right? If you had 1 mole of strong acid, well, 1 mole of this conjugate base is going to react. But we didn't, I don't know what we did. How do you figure out moles if they give you volume and concentration? Yeah, you can multiply. If you can see it, it's just going to be 0.1 times 0.25. But if you don't see that, you should probably set up the big M equation. Right? The big M is the 0.1. Right? The liters is the 0.25. So to get the moles, you end up multiplying just like Kenneth said, the 0.1 times 0.25. Okay, so that's going to decrease by that number of moles. And the number of moles of HF will what? F minus decreases, HF increases by the exact same number, right? 0.025. Instead of adding, here I added this one this morning to make sure you're following me. If we have our HF, our buffer, and we're going to add sodium hydroxide to it, the pH should skyrocket because it's a strong base. But, okay, then the number of moles of F minus will what? why I can't said that? Because you are adding hydroxide. That means F minus isn't going to react. HF is going to react. And if HF reacts, it's going to form F minus. That's why he said increase. Okay. And it'll increase by, how do you do this again? M times, well, liters, yeah. So you'd have, what, 0.05 times 0.05. Just multiply them. And the number of moles of HF will, everybody, decrease by the exact same number. Okay, so that's kind of the workings of it all. But how do you get the answers in the back of the book? They want to know what the new pH is. They're going to say, okay, here's your buffer. You have such a concentration of HF. We're going to add 20 mils of 0.2 molar sodium hydroxide. What's the new pH? Well, we need the equation. So here it is. They call it the Henderson-Hasselbalch equation. This is what the book gives us. But I don't like it because it's not set up to do what we just talked about. The moles of this increases, the moles of that one decreases. You recognize it? Here's our conjugate base. There's our F minus. Our conjugate acid, there's our HF. But it's in terms of brackets. And what were brackets again, Jose? What do those brackets mean? These things. Bracket F minus, bracket HF. Anybody remember? Concentration. Oh, I don't want to go through all this word and tell you what a concentration is. Volumes are going to cancel out, so let's just keep it in terms of moles. And life is so much easier. We'll keep track of everything then. So I strongly suggest this is so much easier. pH is our answer. That's going to be our pH of our buffer. We just figure out the moles of the F minus, figure out the moles of the HF, or the conjugate base and conjugate acid, whatever they are in our problem, and divide the two, take the log, add it to a pKa. All right, well, what the heck is pKa? What's Ka? Where do we get these Kas from? They're in the tables, right? So we'd find HF, and we can find its Ka. Let's just find it in the table. pKa means do what to the Ka? Take the, call it the P function. Kind of like pH is a negative log of the hydrogen ion concentration. pKa would be the negative log of, whatever you find in the table, the Ka. Right? So pKa is just the negative log of the Ka. And that's the number you get from the table, right? You have to look it up. Look it up for our buffer. And remember, our buffer is just a weak acid. Okay. So let's try one of these. So we're preparing a buffer. We added 50 mils of 0.25 molar sodium cyanide to 40 mils of 0.2 molar HCN. What's the pH of the final buffer solution? So it's a buffer. So anytime they mention the word buffer, I'm jumping right to this equation. My modified Henderson-Hasselbalch equation, where I don't have concentration in it. Okay, so all I got to do is, hey, how did I get that? Let's do that pKa part. That should be the easy part, Megan. How are you going to do that? How do you get that pKa part? Yeah, let's do that. Let's get, we're halfway done. Well, a third of the way done. There's 3 things to figure out. 4.9 times 10 to the 10 negative. Take the log of it and negative sign. So I get about 9.31 or so probably. Depends on how many digits you want to carry, right? Make sure you get that on the calculator. These little things are what often bite you. Okay. So right now we have pH is going to be 9.31 plus the log of the moles of the conjugate base. Now, what's the conjugate base in this? NaCN. So let's leave out the Na part, because I like just recognizing the conjugate base and the conjugate acid. The conjugate acid, everybody, would be HCN. Okay, so here's really our equation. But you're right, Kenneth. This sodium cyanide and cyanide are the same thing. You get the moles of sodium cyanide, that's the same as the moles of cyanide. I mean, it's 1 to 1. So it might be easier to write sodium cyanide up there, in fact, because then you can see what to do. How are you going to get the moles of the cyanide? Bowdy, how are you going to get the moles of the cyanide? Excellent. Change the 50 milliliters to liters, 0.05 liters. Then she said multiply it by the concentration, 0.25 moles per liter. Liters cancel. You end up with, what's 0.05 times 0.05 times 0.25. You get about 0.0125. So we've got that number. And then the moles of HCN. Kenneth, how are you going to get the moles of HCN? Excellent. 0.04 liters times 0.2 moles per liter. So we're going to end up with an equation that looks like this. We're going to get 9.31 plus the log of 0.0125 divided by like 0.008, or 8 times 10 to the negative 3. Final answer is, what'd you get? Yeah, what's the final answer? 9.5? Did you guys get 9.5? You can get that. So that's our buffer equation. All we do is figure out the moles of base, the moles of conjugate base, the moles of conjugate acid, divide the two, take the log of it, find the Ka, take the log of that, add those two logs up, and we'll have our answer. The Henderson-Hasselbalch equation. Okay. So pretty much every homework question has this part first. And then you know what they're going to do? They're going to do this part. They're going to take some strong acid or strong base and add it to the buffer to see if the buffer does its job. Now, there's some work to do here, but you could pretty much guess what the answer is going to be. Because it's really healthy to do that, because then you'll know whether you screwed up or not, because it's really easy to screw up. Your answer's got to be around what? 9.5, exactly. But it needs to be a little bit lower or a little bit higher than 9.5. A little bit lower because it's acidic. You're adding an acid. So if you're going to guess 9.45, 9.49, that's where it should be coming out from. Okay, so let's try this now. It's a buffer problem. So we have to start with the exact same equation. pH equals pKa plus the log of the moles of, what do we say, conjugate acid, all over the moles of conjugate base. So we have the exact same starting point. Or the base over acid. Is it base over acid? Yeah, it's base over acid, shoot. Okay. So remember what we talked about before, Cameron? We're adding HCl. So which one of these is going to increase? The conjugate base or the conjugate acid? Or which one's going to decrease? Which one do you think of first? The base is going to decrease. Yeah, it's probably more logical to think of that one first, right? Because you're adding the HCl, so that means the base has to decrease. So we could actually modify this a little bit. We could say initial moles of conjugate base minus the moles of, what would you want to say? You know, put it in terms of English. Minus the moles of the what is it? The HCl. Because that's a decrease. So Cameron's exactly right. The conjugate base has to decrease because it's going to react with HCl. So we'll take our initial moles of conjugate base minus the moles of HCl added. Where do we get this initial moles of conjugate base from again? Didn't we do it already? Yeah, it's the 0.0125. That's the 0.0125. The moles of HCl added would be what? How do you get that again, Jose? How do you get the moles of HCl added? Exactly. 0.1 times 0.0. 0.1 liters times 0.01 moles per liter. That would be that one. We want to get the conjugate acid in the bottom. Now, how are we going to modify that equation? Mia, what are we going to do down there? Because this conjugate acid should what? What are we going to write down here? Up here, we kind of made a game plan. How are we going to modify the denominator there? Because up on the top we took, okay, here's our initial moles of conjugate base, and it has to decrease by the moles of HCl that we added. Okay, the denominator, the moles of conjugate acid, has to increase. So we better write a what sign? A plus sign. Keep going, you're on the right track here. Plus, how much? Whatever we got right here, right? The moles of that strong acid, plus the moles of HCl added. Okay, and we have these numbers already. We know that the moles of HCl added, Jose said that was 0.1 liters times 0.01 moles per liter. And our initial moles of conjugate acid, I think we said that was 0.008 from above. pKa, that didn't change. That'll be the same number. See what you get. pH shouldn't change by much. some meat. So what did you get? I got around 9.42 or so. Maybe I'm just carrying more digits than you guys or something. So you got? So watch, I'd especially be careful with this part, right? Because it's easy to screw that up. So this is one of those spots where I really don't do everything in the calculator. I kind of have an intermediate step. Otherwise, I end up screwing up. Because that parenthesis thing, ugh. But it did go down a little bit. Good deal. Okay, so good luck with the homework. Come by and be glad to help you out.